As you might have noticed, there are a lot of formulas involving the dot product and the cross product, particularly the dot product. So I want to highlight is kind of what are some of the more important formulas and just give you some practice setting up problems using these formulas. So without further ado, probably one of the most important formulas is that the dot product, if we take a vector and we dot it with itself, we get the norm of the vector, or its magnitude, squared. Remember that squared sign, it's important. What you also might see this as is that the norm of the vector equals the square root of the vector dotted by itself. Let's make sure we have arrows just to remind ourselves we're talking about vectors. And again, this sign just means this is the magnitude of the vector or the norm of the vector. I will probably say either of those interchangeably. And with that, we also have a nice, so I'm going to star this because that one is very important. We also have an alternate formula for the dot product between two vectors. And that is that we can calculate it by taking the norm of the two vectors and multiplying by cosine of the angle between them. Now, this one isn't as important, I would say, from a memorization. You'll use this for the rest of your life, but it's really good for understanding the geometry of what's going on with the dot product. So I'm not going to star it, but it is an important thing to know. It also helps us find the angle between two vectors. If we just solve this for theta, we get that theta equals the inverse cosine of let's see, we would have a dot B. Keep forgetting some of my arrows, but that's okay. Times the norm of A times the norm of B. And that's just solving this equation for theta. So that's also good to know. Again, maybe more from what it tells us about other things and for setting up problems in context. But I would say that it's less important than the one before. Another reason why I wouldn't highlight this one as much is because there's a very key formula that we get once using this property, and that's the formula for the projection of B onto A. If you don't remember, what this means is that if we have a vector A and a vector B, basically it's asking how much of B works in the direction of A, is essentially what it's asking. So that would be the projection. This new vector here is going to be the projection of B onto A. So that formula is a little bit complicated, but what it's going to be is it's going to be A dot B over A dot A. You could also think of this as the norm squared, all times A. So what I like to remember for this is that even though B is the big letter here, pretty much everything else is A. So that kind of helps me remember how this formula is set up. So the projection is very important. I'm not going to star it because more often than not, what we do use and what we care about more is the norm of the projection. So often we don't care what this vector is necessarily, but we care how long it is. So the norm of the projection, well, essentially it is, you could take the norm of this, but what that really does is, this down here we said is the norm squared. This is just a constant. And the norm of this is the norm, so what you're going to end up getting is just A dot B. And then since we have the norm squared down here and the norm up here, one of those is going to cancel. We're just going to be left with the norm of A. And this I will star because, as I said, a lot of times we care about the norm of this new vector, especially when we get to distance problems. That's going to be important. Future Andrew dropping in really quick to say, those were not supposed to be, there's a lot more on the screen now, those were not supposed to be parentheses, those were supposed to be absolute value signs, because if your value were negative, well, we're looking at lengths, and we want to make sure we have a positive value. Okay, carry on. Okay, so those are some of our key formulas. Another key formula, I hesitate to put this here because it doesn't really use the dot product, but a lot of times we'll normalize vectors. Because a lot of times we care what happens when this vector's length is 1, because vectors with length of 1 are really nice to work with. So to normalize a vector, you just take it and you divide it by its norm, which again we could define in terms of the dot product if we wanted to. So we have that, which is also important. And as far as context goes, one of the contexts that we'll see a lot is work. And work says that if I have a force acting on an object, so we'll say the force is something like this, and my object moves this far, we say this will be the displacement vector from P to Q. So if you have, and notice this force isn't really pushing in the direction of P to Q, but you could see how this might relate in terms of the projection. And since the projection is involved, that might key us in that we're going to have a dot product. What it turns out is that the work is going to be equal to, it's going to be a value given by the force vector dotted with the displacement vector. And that's going to be something that we will see a lot, especially near the end of the semester. And one nice thing to realize here is that if this gives you a positive value, it means that the object is moving with the force, and if you get a negative value, it means the object is moving against the force, so against force. If you get a value of 0, well, what's happening? It's kind of like asking if I'm trying to push a box across a floor, and I'm only pushing the box up, it's not going to get across the floor. So we're not really doing any work. That is kind of what we have there. So those are a lot of formulas, but hopefully we can kind of remember some of the key ones. And now let's go to the cross product. I'm only really going to star one of the cross product formulas because there's only one that I really care about, and that is that the norm of the cross product is the area of the parallelogram parallelogram between, I'll put that in quote marks because that doesn't really make a bunch of sense, A and B. Go ahead and put some of those lines there. And what it basically just means is if I have A here and B here, then here's my parallelogram, and the cross product gives me the area of that. So that's nice. And so I'm going to star that. For that reason, that also means that the norm here of the cross product is going to equal the norm of A times the norm of B times sine of theta, which is nice. And that, again, is something that will help us in kind of creating these context problems. And then we have two specific contexts that we look at. One of these is the torque. So if I have a lever of some sort with length, we'll say this is r, this vector represents the kind of source of rotation. So if this represents the object and we exert a force going like this, then the torque vector is going to be given by this vector r cross f. It's going to point perpendicular to those two, so perpendicular to kind of the plane of rotation. So, and then its magnitude is going to be the amount of torque. So that's something we will have. So the magnitude r cross f is the amount of torque. And then there's another one that we had, which was the velocity of a rotating particle or a rotating object. So if we have something that's rotating, let's say we have, here's our axis of rotation. I'm not going to draw a line there. If we have an axis of rotation and some object located at this point, we'll call this point R. Then we want to kind of find the velocity of this thing. So what we're going to do is we're going to define a vector. This is an omega. And what omega represents, omega is a vector. These are both vectors. With magnitude given by the angular velocity is the angular velocity. So basically, how fast is this thing spinning? And then it points along the axis of rotation. So the reason why this formula can be a little bit hard is just because one of the parts of this formula is something weird. So if we want to find if we're spinning with the magnitude of omega and our particle is located at this r vector, or at the tip of this r vector, then the velocity is going to be given by the cross product of omega and r. And it might not make a whole bunch of sense why that would be the case, but if you look at the definition, basically we defined omega in a way so that we get the answer we want when we do this. So that's nice. So we have that. And that formula, again, is good for when we have an object that's rotating and we want its speed. So torque is, I'm trying to rotate an object, how much force do I need? Whereas velocity is, I have an object that's already rotating, how fast is it going? So, and I've said speed when I meant velocity a few times, so, you know, forgive me, that's a sin in vector calculus. So anyhow, we have all these different formulas, and you're going to need to really remember some of these, like know that the dot product and the magnitude are very closely related. know how to take the projection, or at least the norm of the projection. Know how to normalize vectors. I forgot to star work. Work is also important. And also remember that the cross product gives us the area of this parallelogram. These applications like torque and velocity are less important. We're just going to use them as examples of what the cross product tells us, but we won't do a bunch more with them in this class. So there you go. There's a whole bunch of formulas involving the dot product and cross product. But wait, there's more. There is a secret bonus formula, which I kind of just forgot to talk about even though it was in my notes. And that is that we can actually combine the cross product and the dot product to give us a new thing. If we have three vectors, A, and B and C, and we take A cross B and dot them with C, the magnitude of this is going to be the volume of the parallelepiped, so volume of parallelepiped. And don't judge my spelling here because I don't know how to spell that word. That O might be an E. I couldn't really tell you. So it's going to be the volume of the parallelepiped we get by kind of just putting all of those vectors together at a common origin. So if that was A, this was B, and then C kind of went off in this direction, let's say. Let's say that's C. This is going to be a fun picture. Yeah. And it's going to be the volume of this thing. So, oh, it just got worse. That's okay. You can judge my drawing personally. So yeah, we get this nice thing. And yeah, that kind of combination of cross product and dot product gets you that. In fact, if you get rid of those absolute value signs, we get something that we call the scalar triple product, if I recall correctly, which is just a nice thing. It's a way that you can take three vectors and kind of put them together to get some scalar value. So there's your bonus formula. It's not that important.